Right, so, and I'm going to put you on mute for.
¿Tienes comida, señor?
Here we go. Right, well, good evening, everyone. I kind of promised you a hard time today, not because I'm wanting to make it hard for you. It's just going to be hard. We are slowly getting to the end of this. 1110 is the hardest section in chapter 11. The last one, applications, is actually not that bad. And once you've gone through this, you're good. So essentially, we're dealing with Taylor's and Maclaurin series. We've got a whole bunch of questions. We've done a lot, but there's still a lot more to do. And I want to focus, based on some questions I've been given, I want to focus a little bit more on it than I typically was planning to, but that's fine. So what we are going to be doing are creating Maclaurin series from scratch. Not many of them. I'm only going to do question 7 because we have had lots of practice of that. And the trick to making this happen isn't it looking for patterns and finding a pattern for the nth derivative at 0. If you can figure that guy out, then yeah, you're done. We've done a little bit of this. We're going to do a little bit more, where we're going to still create Maclaurin series, but we are going to use pre-known ones, right? Ones that someone has already found. You don't need to frantically write these down because I've put this thing here into Canvas. So you can just go to Canvas and print this out. You'll have essentially everything you need to know, including, as an added little bonus, the radius of convergence. So it's got most of them. The only thing that looks like it's missing is 1 plus x. And I don't think you're going to use that one, which is a binomial theorem. But everything else here can get used and will get used in that group of questions. And so when we come to do question topic 2, that's questions 8 to 13, we're really just going to do a glorified version of, you remember these guys, where you just did substitution, so you could use them to find x squared over 1 plus x cubed, that kind of thing. We will use that technique, and we've done a little bit of that, to find power series, but not from scratch, but by using these guys and then some substitutions. And then we've got a little find a Taylor's polynomial Tn number 14. That's a one-off question because actually in 1111 you do that a lot. So I guess it's a little orphan. And then we kind of reset the clock and we start again, but much fewer questions. We're now going to do Taylor's series of a function centers to x equals a. And the formula for that is identical to this, except instead of 0, you get a. Instead of x, you get x minus a. And this thing means the nth derivative of a. So in these questions, you're trying to find a formula, a pattern for the nth derivative of a, because once you know that, you plug it in. And then you have a couple of application questions at the end. And then the next section is all about applications. But many of them are going to be Taylor's polynomial applications. So that's a kind of big picture of what's going to happen. Let me get started with our first one. Have I set it up right? No, I haven't. Give me a moment. Get caught off guard there. That's not the guy I'm looking for. Where are you? There you are. So I'm going to do from scratch the Taylor series for 3 to the power of x. Now, since it's Maclaurin series, I should say, we're going to find that guy. Here's one. And then we're going to find the derivative, first derivative. Now, if you differentiate 3 to the power of x, yes, you do get 3 to the power of x, but that's not all you got. So let's get some cobwebs out here. Can anybody remember what you also multiply by?
Multiply by x, right?
Nope. Think again.
Do we multiply by the natural log of 3?
You do indeed. And if you find the first derivative at 0, you get natural log of 3 times 1, which is just natural log of 3. So I'm now going to do the second derivative. which basically is that guy times another natural log of 3. So I'm going to call it the natural log of 3 squared, 3 to the x. And so the second derivative at 0 is going to be the natural log of 3 squared times 1. I'll do one more. I think we should have figured out the pattern by now. What will the third derivative be based on what you've already seen previous?
ln 3 to the third power.
Yep, times 3x. And the third derivative at 0 ends up being that guy cubed times 1. And then the kind of hardest part, we have got to figure out what the nth derivative at 0 might be. Well, think of that as being the first derivative. There's the second derivative. There's the third derivative. We want to know what the nth derivative would be. Right, second derivative is this guy. Third derivative at 0 is this guy. What would the nth derivative at 0 be, looking at the pattern that you can see?
Natural log of 3 to the power of n, I assume, right?
And you would be assuming correctly. Does that make sense, everybody? That is the guy that works. That's always, in my opinion, that's always the hard part of this. Just finding that. Once you find that, it's really just plug and chug, virtually. So Maclaurin series says that its series is n equals 0 to infinity, the nth derivative at 0, x to the n over n factorial. And once you know what that guy is, you're pretty much over. Are we comfortable with that one? That is pretty much us done. All I want to do on getting Maclaurin series from scratch, right? Doing it this way, this is from scratch. The next bunch of questions, which are 8 to 13, and we've done some of them, I just want to do some more, is create a Maclaurin series for a function, but using known power series. And these are questions 8 to 13. So let me pick one at random. Here we go. Question 9. We are going to find the power series of 9x, the cosine of 1/2 x squared. So here we go. The cosine function has this power series here. Oops, bring it over a little bit. The cosine function is this guy here. Now, if I want the cosine of 1/2 x squared, I have to adapt. And the adapt tends to be substitution. So I'm going to go n equals 0 to infinity. The -1 to the n is not going to change. That 2n factorial on the bottom is not going to change. And what is going to change is, see this x that's here? It's a placeholder for that x. So if you put 1/2 x squared here, where this x goes, you put the same thing, 1/2 x squared, then you raise it to the power of 2n. Are you comfortable about the substitution method that I used there? Using the fact that I know what the cosine of x power series is, and I've adapted it to find the cosine of 1/2 x squared. Right, if that had said 5x, wouldn't I put a 5x in the brackets? If that had said 2 million x, I would have put 2 million x in the bracket, right? If it said square root of x, right, I would have put square root of x in the bracket, right? That's how you do these. So moving to the next stage then, and it's style points. Not going to do anything with that guy. Not going to do anything with that guy. This fella here is 1/2 to the power of n, and this guy here is 2 times 2, so that gets you 4n. I don't like a half n personally. I think it looks clunky. So I would rewrite the 1/2 to the power of n in a slightly different format, but I think a slightly prettier format as well. Are we comfortable so far with what we've done? Are you happy about that 1/2 turning into a 2 to the n in the bottom? Because 1 to the power of n is just 1, so it doesn't really matter, right? Now, the only thing left is bring these two guys inside and we are done. And I'm not going to do anything with that 9 except write it down. And then I'm going to do an x and add 1 more power because of that guy. And then everything else really gets written again. So we have just done from scratch the power series of f of x, which was this guy. Yes.
When you created the 1/2 to the n, shouldn't it have been 1/2 to the 2n?
Whoa, thank you. Yeah, fixed. Yes. Fixed. So 2 to the 2n rather than 2 to the n. Are we good? Right. Try another one. Let's do this one. No particular reason. I'll do 11. And in question 11, we are being asked to create a power series for that guy. So I'm going to look over here and find the 1 plus x guy, which is him. And I'm going to realize that the x is now x cubed. So it's going to be x squared, this power series here. So it's sigma n equals 1 to infinity, -1 to the n minus 1. Instead of x to the n, it's x cubed to the n. And the whole thing is just over an n. Not really a lot of tidying up here. I like the whole thing over n, it just looks right here. You know, right to me to write it that way. And just bring in the x squared and we're finished. And multiplying by an x squared really just adds on an extra 2 to the power of x. Are we comfortable with how much easier it is to create Maclaurin series when you can use pre-built ones and substitution? So what that does is it expands the number of functions we can do a Maclaurin series for, because they are really hard to do from scratch. Can you just trust me that if you found the first, second, third, and fourth derivative of that, you'd probably be hard pressed to get the general formula. I mean, I'm not saying you couldn't, but I think it would be extremely ugly, because just think of what's going to happen. When you do the first derivative, aren't you going to have to do a product rule? And isn't there going to be 2 pieces, one of which is a fraction and the other is not? You're already in trouble algebraically, aren't you, by how ugly the first derivative is? But won't the second derivative be twice as ugly? And the third, I mean, just process-wise, doing it from scratch is really not feasible. So it's lucky that we are allowed to do this substitution trick that kind of makes the job, in my opinion, 10 times easier. So who we got? Might as well pick 13. It sounds like the last one. Too easy. Too easy. Okay, well, I will pick 13 after all. They're not that difficult, the ones that are in that list. So we are going to be trying to find the Maclaurin series for that guy. And my cosine function is this one here. This one here. So it's going to be sigma n equals 0 to infinity, -1 to the n, not x to the n, but this guy instead of x. So x to the 4 to the 2n, all over 2n factorial. This should be a one-liner. I don't think I need to do much. You agree that one actually was pretty easy? Any questions so far about using pre-built ones to create power series for other functions such as this one? Does the process seem reasonably logical? Which is good. Okay, you might think, well, you haven't held your end of the promise that your life is going to get really difficult. It is. We're just taking what, little respites we can.
Feel free to break that promise.
I wish I could. Right. Now, we have this little one-off guy, finding a Taylor polynomial. So a Taylor polynomial like T4 is basically just a Taylor series, which is n equals 0 to 4. And it's the nth derivative at a, x minus a to the n over n factorial. Now, I've got that written somewhere, haven't I? No. I'm sure I had it yesterday. Can you remember the general formula for Taylor series is this guy? Taylor series just makes that infinite. A Taylor polynomial stops at, in this case, 4, right? T4. And didn't we do yesterday, we done like whatever it was, T3 and T4, and showed you how accurate those things were. Remember that? Okay, so in this question, number 14, you have a function and you're going to find t, whatever they ask you for, what they're asking you for. They're asking you for T3. So you start off with the original function, which is 8 over 1 plus x, and it's going to be centered at 2. Well, I'm not even going to attempt to do that guy in the format that it's written. I'm going to call it that guy, which is actually the same thing, right? Now, if you want to find the value at 2, it's 8 over 2 plus 1, 3. So the answer is 8/3. If you find the first derivative, you multiply by the power and you reduce the power by 1 and you get that. And you find the first derivative at 2, which is going to be negative 8 over 3 squared. So it's negative 8 over 9. Since I am not looking for a pattern here, I'm not going to write that down as 3 squared. That's what I would be writing down if I was trying to create a pattern. But since I only need to go as far as the fourth derivative, right, I want, to calculate it and simplify as much as I can. So if you want to do the second derivative, you multiply by the power, and then you reduce the power by 1. And if you find the second derivative at 2, that's 3 cubed, so you get 16 over 27. And what did I say, 4? Okay, I guess I have to keep going a little bit longer. For this one here, it's negative 48, 1 plus x to negative 4, and the second derivative at 2 ends up being negative 48 over 81. And our last guy is, it's already getting ugly, isn't it? 48 times 4. Correct. So it's 192, 1 plus x to negative 5, and the fourth derivative at 2 is positive 192 over 243. And thank goodness we can stop here. Now, if you wanted to do T4 of x, what you're essentially calculating is this guy. The value of the function at a plus the derivative at a, x minus a, all over 1 factorial. And then the second derivative of a, x minus a squared over 2 factorial. The third derivative of a, x minus a cubed all over 3 factorial. And lastly, if I don't have enough room, just pretend that you can see some of it. But yeah, I guess I just got it right. A is going to be 2 in this case. So these A's here are going to be 2s. Oops. T4 of x then is the value of the function. So it's 8/3. That guy is 8/3. Plus, well, it's actually minus because it's a negative. 8/9 x minus a, because 1 factorial is 1, so it doesn't do anything. The next one is a positive, and it's going to be 16/27 x minus, I'm calling them a, but it should be 2, x minus 2 squared over 2 factorial, which is that guy. Then it's going to be negative 48 over 81 x minus 2 cubed over 3 factorial. And the last one is 192, 243 x minus 2 to the power of 4 all over 4 factorial. That is Taylor 4. That's what Taylor 4 looks like, centered at 2. Do you agree it's ugly? So here's the good news. No, you don't FOIL that whole thing out and make a polynomial. So you leave things as x minus 2 cubed and x minus 2 to the 4. That's good news. Bad news is I'm not finished yet, because some of these guys cancel, don't they? And I have to simplify them down. So over here, because I want more room, T4 of x is 8/3. Take away 8/9 x minus 2. 2 and that cancels, so I now have 8/27 x minus 2 squared. This guy, that's 6, God in heaven, 6 and 48, that's a lot of things. I'm not going to try that. I got 48 on the top, and it's going to be divided by 81 times 3 factorial, which is 6. And then I'm going to make the answer a fraction. So it's 8 81s. So let's just let the calculator take the strain, right? And the last one is 192 over this combination. So 192 divided by 243 times 4 factorial, which is 24. And make the answer a fraction. And that's 8 243s. And that's what T4 of x looks like in all its glory. If I put the original function, which was this guy, and I sketch, which I'm not going to do, that guy, and I did it in Desmos, as long as I stick close to 0 and keep away from -1 especially, so maybe, you know, go as close as 0.8, maybe 0.8. So imagine in that part of the world, the curve looks like this, right? Nothing weird happening. T to the 4 would look like this. Can you imagine it would almost be a perfect fit? Right? Now, what is the problem at x equals -1, and why am I avoiding that like the plague in my little description of what that would look like compared to this function? What's the problem at x equals -1?
Indefinite if 1 minus 1 is equal to 0.
Right. And what does that graphically look like? A vertical asymptote. Would you agree vertical asymptotes don't play well with anybody? So yes, we have a power series, and this is just T4, but I could do a Taylor series, you know, if you gave me a couple of $100, I might do it, but I'm not doing it for free because it'd be horrendous to do. But I could do a power series of that. But wouldn't my power series only be good in a certain interval of x's? Remember those interval of convergence that we talked about? They're not just there for cosmetic reasons. Aren't they there to protect your power series? Right, so I bet you this one would have an interval of convergence that wasn't 1. It'd be less than 1. It might be a 0.5 or something, right? And as long as you keep within that range, everything's fine. But if you go anywhere near this guy, and all bets off, right? That guy there, not even on a good day, right, would be equal to the thing. And I've just realized something I should have noticed. This is centered at 2. So what I said is still true, but the function's over here. When you are centered at 2, it means you're building from 2 outward. So as long as you're close to 2. So the argument I gave for this one would be for a Maclaurin series. And the argument I'd give for this one is for a Taylor series. Still the same thing, right? You need to keep close to the center. At least you got a bit more wiggle room in this version. Oh, and what did they ask you to do in WebAssign? Well, do you see this answer that I just gave? Right, this one here. WebAssign doesn't want you to write it that way. I wish they did. They want you to write it as 8/3, comma, that guy, comma, that guy, comma, that guy, comma, that guy. As a comma separated list. So you just write down each piece with a little comma beside it. I have no idea why you want you to do that. Wouldn't it make much more sense just to write it as it really is? But maybe that's just to do with programming, right? It's easier for it to check when you write it that way. Well, any questions about the one example that we've got, which is finding a Taylor polynomial? It basically, you just, you find the first 3, 4, 5 derivatives, whatever you're being asked. Okay, now we're on in mega time.
So polynomials have to do more with derivatives.
What was that you said, Lewis?
So do polynomials have a lot more to do with derivatives?
I'm not sure what your comment is about. Are you saying that?
No, I'm asking, do polynomial functions always have more to do with derivatives?
I'm not really sure to answer that. I guess it's because I'm old and not sure. Power series are polynomials, and all functions can be written as infinite power series. So in that sense, there's polynomials. But are polynomials connected to derivatives? I'm not sure what that means. Sorry. Has someone else got an idea of, it's not his fault, it's my fault not understanding the question. Does anybody get an idea what he's getting at?
Maybe are we doing a lot of derivatives when we're solving these problems?
Oh God, yes, you are doing an awful lot of derivatives. And all your derivatives end up being polynomials, right? They all end up being powers of x squared and x cubed, or x minus 4 squared and x cubed. Yes. So to your answer to your question, yes, there is a lot of there's going to be a lot of polynomials when you do derivatives of power series. In fact, and all the answers polynomials in some sense. Right.
Thank you.
You're welcome. Now, from scratch, always the hardest way to do it. Taylor's adds in one extra dimension, but there are only 3 examples. So I'm going to start with question 15. And we have a function, which is a natural log of x. And we are going to be doing a Taylor series centered in this case at 8. Right. So I'll start basically repeating myself, which is this guy. And then the function 8 is the natural log of 8. Okay, that's not bad. Then we find the first derivative, and that's just 1 over x. And so the first derivative of 8 happens to be 1/8. Now, if you want to write that guy as x to -1, it helps for differentiation. Second derivative then is you multiply by the power and then you reduce it by 1. And if you simplify the answer, can you trust me, that's what you get. You get -1 x to -2, and I'm writing it like this. And the reason I'm writing it like this is it just makes the answer cleaner to see. Right. Now, if I do the third derivative, you end up with a positive 1 times 2 over x cubed. Can you trust me on that? It's what you get when you tidy it up. And so the third derivative of 8 is positive 1 times 2 over 8 cubed. You notice you never do the calculation, right? You don't write down what 8 cubed is. You leave it as a calculation, 8 cubed. Anybody want to have a guess at what the fourth derivative is going to look like in terms of x?
That negative 1 times 2 times 3 over x to the 4, right?
I agree with you totally. And so the fourth derivative of 8, and I should mention there's a minus there. I'm sure you meant to say that. -1 times 2 times 3 over 8 to the 4. I think I've done enough derivatives to figure out the nth derivative at 8. That's the guy we need. Because if you've got this guy, don't you just plug it in here and you're done, right? That's the hard part. There's definitely a lot of things going on here. First thing I'm going to tell you is ignore the log 8. It's an anomaly. Don't worry about it. We'll fix it in a minute. Just focus on n is 1 gets you an 8th. N is 2 gets you that guy. N is 3 gets you that guy. N is 4 gets you that guy. So what would you get when it's n?
N factorial.
I agree. Would you agree? Well, whoa, wind up. Are you sure it's n factorial? Let's check it out. The third derivative is actually not 3 factorial, isn't it? Only 2 factorial.
So n factorial minus 1 or n minus 1 factorial.
Agreed. Yes. N minus 1 factorial. Okay, we got that one. Let's look at the powers of 8, because there's clearly a pattern here, isn't there? Third derivative, 8 cubed. Fourth derivative, 8 to the 4. Nth derivative.
To the n.
Right, great. Now, it is there, although it's not maybe too clear. Do you see plus minus going on? And we've seen plus minus before. And isn't that generated by -1 to the n or -1 to the n plus 1? Or if WebAssign's been really a pain in the butt, -1 to the power of n minus 1, which does essentially the same job. Now, looking at the pattern here, 1 gets you a positive answer, 2 gets you a negative answer, 3 gets you a positive answer, right? And so on and so forth. Is that going to be a -1 to the n or a -1 to the n plus 1? That's your choices.
It is belong to the n plus 1 or the n minus 1.
Okay. And I'm going that way because I like n plus 1. We're done. Haven't we created a Taylor series, at least the bit that's important, the nth derivative of 8. So now you go over here and you say, okay, the Taylor series centered at 8 will be sigma n equals 0 to infinity. Check. The nth derivative is all this stuff. Right, that's that bit. Within x minus a becomes x minus 8 to the n. Oh, and an n factorial as well, right? Because that's always going to be there, right? and so on and so forth. Now, that is very close to being the final answer, but it isn't the final answer. It's going to go here. I don't think I can do anything with that piece, but I think I should be able to do some simplification there. Would you agree? N minus 1 factorial on the top is going to cancel with an n factorial on the bottom, right? N minus 1 on the top, n factorial on the bottom, right? They cancel out. What's left? And does it go on the top or does it go on the bottom?
And on the bottom.
Great. And while we're doing it, can't we stick the a to the n on the bottom and put an x minus 8 to the n on top? Yeah. Is your brain hurting? Are you still with me?
We distribute the n and get rid of the an.
Can we distribute the n?
In the top, you see how it's x minus 8n?
Oh, that's x minus 8 to the power of n. You can't really do anything with that. So don't do anything to that. Basically leave that alone all the time.
Okay.
Nothing you can simplify it by. We could simplify the factorials, that's fine. But no, yeah. Oh, actually, guess what? We have a sign like to n plus 1. Who knows what it's going to like tomorrow, but that's what it liked. So I like the fact that it liked that. Right. Do one more of these and then I'll talk about how you can use known series to create Taylor series.
Oh, Professor,
Yes.
I was wondering, why was it n plus 1 in the last example?
Oh, okay. If you take this guy and you plug in a number like 2, right? So if it's 2, shouldn't it be negative? Let's see what happens. Well, negative 1 cubed gets you negative. That means it works. If you plugged in n equals 1, right? We know it's one of the other. We know it's negative 1 to the n, or we know it's negative 1 to the n plus 1. Sometimes it's just easier to put in 1 and check it. Oh, that one didn't work. Okay, it's the other one, right? So put in negative 1 to the n and check it. And if it doesn't, change it. If it does, keep it.
That makes sense. Thank you.
You're welcome. 16. The function is e to the 2x, and it's going to be centered at 4. So I'll start with my function, e to the 2x, and the value of the function at 4 ends up being e to the 2 times 4, which is e to the 8. When you differentiate, that is not just the answer. What's missing? The derivative of e to the 2x is not just e to the 2x. What goes here? What's missing?
It should be a
2.
2.
Should be a 2. And so when I find the first derivative at 4, you're going to get 2 times this guy. So you're going to get 2 times e to the 8. You happy with the e to the 8 just being there all the time now? Now, if you do a second derivative, you're going to get this guy times another 2. And I'm not going to call it 4. I'm going to call it 2 squared. I think I should get away with just one more. If you differentiate this, you get 2 cubed e to the 2x, and the third derivative at 4 ends up being 2 cubed e to the 8. I think this pattern is actually a lot nicer than I thought it was going to be. Okay. 1 gets you this guy, 2 gets you this guy, 3 gets you this guy. So far, so good. What would the nth derivative evaluated at 4 get you?
2 to the power n to the e to the 8 times e to the 8, sorry.
Yeah, I knew what you meant. Would you agree with that, guys? Third derivative 2 cubed, second derivative 2 squared. So you should be able to then do a Taylor series. N equals 0 to infinity. The nth derivative at 4 times x minus 4 to the n all over n factorial. In this particular case, nobody cancels with anybody, so I guess we're finished, right? There's nothing to tidy up. And I've missed a fella out because I get too caught up in the process. You remember this guy, and I said, you know, he's an anomaly and forget about him. Remember that? Well, I can't forget about him forever. I actually have to start at 1 because I started my series with only 1, 2, 3, right? I didn't use 0 in it. So what's missing? Well, what's missing is just that guy. So you just stick him at the front, right? Log 8 and call it good. So if especially the value of the function, right, on the first term, sometimes they don't work with the rest of the power series. So what you do is you get the rest of the power series, in this case starting at 1, get your formula, cool, and then just stick this guy. So see if this guy is no, e squared or 1/2 or 42, just put, you know, e squared 1/2 or 42 plus the power series. And so maybe it looks a little bit awkward, but that's what you do. And very often, if that first term does not follow the pattern, would you agree log 8 has nothing to do with what comes later? And isn't that a good sign that you shouldn't be using it in your rule, right? You should ignore it and just stick it in as an oddity at the beginning. If it does happen, it only tends to be the first term, right? This guy. The other one didn't have that problem, so I used it all the way through. Now, how to find Taylor series by using these guys. Okay. So, suppose I wanted to do a Taylor series of this function, and I wanted it to be centered at 1. Now, I know what e to the x is. So far, so good. So I want to know what it would look like at 1. Not quite the fit I was hoping for, agreed? So do you see that you can't use the formula in a substitution way? Because if you make this x minus 1, aren't you really just getting the power series for this guy? You're not actually getting a Maclaurin series. Even though it sort of kind of looks like one, that is not the way it's going to turn out. So you have a little bit more work to do. And essentially, who shall we pick? We've got 17. Have I done 17? No, I've not done 17. Let's do this guy. That's him, right? Would you agree that every derivative, including the nth derivative, is e to the x? You agree? Now, every derivative is e to the x, so won't the nth derivative at 1 just be e to the 1? That guy is the missing piece of the puzzle. So you can use this piece of the answer, but what's important is you need to get this guy, right? And so what I've actually done now is I've done a Taylor series. So if you want to create a Taylor series, you have to figure out what this guy is. And all the other pieces kind of come together. You're not going to save a lot of work, to be honest, but that's how you would do it. Of course, you could just do it from scratch and get the answer that way, can't you? And it would be the same. Now, a couple of little application guys, and we are done with this section. And then we move on to the section 1111, with that luck. I've lost my guy. Where's my little list? Oh, guys, have I shared with you that I'm actually addicted to brake fluid? No? But it's okay, because I can stop anytime I want. Oh, come on, Maxwell, that's a good one, right? Cam,
I think
I need some backup. That's a good joke.
It's a good dad joke.
It's a good dad joke. Okay.
Ha,
You've
ha, 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 ha.
No, I'm not taking sympathy laughs to get it.
I'll give it to you this time.
Okay. I'll tell you the other one. Well, I can't find it, but I know what the two questions are. They're the last two. So, what's the other ones in my head? Did you hear about the two high school students that get caught in the high school, sports ground at night by the police? And when they found them, one of them was snorting gunpowder, and the other was drinking right out of a battery acid. So they got arrested, and the next day in court, do you know what happened to them? One of them got charged, and the other was let off.
Did one die?
I'm going to mute you, Jeremy. You're just not going with the flow here. Okay. I don't know if I've actually kept my promise. Did your brain hurt today, or were you still with me? Okay, kind of, sort of. Okay, half kept my promise. That'll work. Right. So, first application question that we're going to look at is how can you use Maclaurin series to find limits, like the limit as x tends to 0, of 1/3 x cubed, take away 1/2 x squared, plus x, take away the natural log of 1 plus x, all over x to the 4. And we could certainly, yes.
is the next approach is 0 or infinity?
It's 0.
All right.
I wrote down infinity, but I was scanning the wrong question. So it is 0. Now, I could actually do this without resorting to one of these guys, right? I could do it simply by doing L'Hopital. I think I'd have to do L'Hopital 4 times, which I agree it'd probably take 4 times. So it's doable, but I'm going to do it using these guys. So I'm going to do this fella, take away this fella, plus this guy, minus that guy. Now, I'm not going to write all of this guy down, right? That's not what I'm going to do. I'm just going to look at the log function, which is this guy here. Do you see these terms here? And I'm only going to write it down as far as x to the 4. And the reason I'm doing that is because of this x to the 4, right? If this had said x cubed, I would have written only down to x cubed. You see the first 3 terms. So the log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, right? And I know that's not the whole of the log function, I guess technically ... But I can combine the top answers together. And let's see what we get. And And what do we get? Well, we get this guy, take away that guy. Oh, they're gone. And I get this guy, oh, add that guy. I get this guy, take away that guy. Actually, don't these three get killed off by those three? And what we have left is a negative x to the 4, 5. If you wanted to see what the next few terms would be, that's a 4, by the way. You'd get that guy, and then you'd get that guy forever. All over x to the 4. Are you still with me? I just written a few extra terms down. Right, that's the last one, but if you next two terms, it would look like that. And now I'm going to divide each of these with x to the 4. So what I get is negative a quarter plus x over 5, take away x squared over 6, plus or minus a whole load of other things. Still with me?
You'll just be left with the negative 1/4, wouldn't you? Because if you plug in 0, cancel everything out.
Good. And wouldn't everything else be x cubes and x sevens and x to the millions, but won't all of them be zeros? And therefore, we have now found the limit. An interesting way of approaching that problem. Great. Now I'm leaving that one for you. That'll be fun. I'll do a basic one instead. All right. I'm not quite sure where you probably met this one. I know I've seen it in 141 occasionally, or at least 142 maybe. But do you know sine x over x as x tends to 0 and can be done with L'Hopital? And if you do it, can you trust me the answer is 1, right? Let's try and do it this way. So it's going to be the limit as x tends to 0 of the sine function. And this is the best fella to use. So it's x, take away x cubed over 3 factorial, plus x to the 5 over 5 factorial, plus or minus a load of terms I'm not really interested in writing down. And so it's now going to become the limit as x tends to 0. Well, don't need a fraction here. 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial plus or minus a whole of the other guys. And don't all of these disappear to 0? And there's your answer. So you could use power series to find limits. Now, the ones you've got are really quite nice ones, but can you imagine that the functions that you got would be really horrible functions? I'm not going to do this one, but it would be fun, I guess, to try and do it. I could find a power series for that. Or at least couldn't I first find the first 3 or 4 terms, right? A T3 or a T4. And then I would be able to find out what this is equal to. By the way, if you want to find out what the answer to this is equal to, it's 1. But anyway, can I do it with maybe writing down what 1 plus x squared is, you know, T4 say, all divided by x. If you try to do this guy using L'Hopital's rule, isn't the square root of 1 plus x squared a problem? Because when you differentiate it, don't you get a 1 plus square root of 1 plus x squared on the bottom with a times 2x? So can you imagine all you end up doing is getting various versions of that alternating forever, in which case L'Hopital dies on you. Now, if you wanted to know what that guy looks like, not as a full power series, because it wouldn't really work, but couldn't I at least do the value of the function at 0, the derivative at 0, x over 1 factorial, the second derivative at 0, x squared, maybe over 2 factorial. That's probably enough terms. Couldn't I just do a T2? You know that it's a T2 because it's an x squared there, right? And this is a T2 evaluated setting it at 0. I could find that. Plug it in the top. Won't the x's cancel out with various things? And I should, with a bit of luck, get an answer. So we're now moving on to our final section. And I'm getting the number, I believe it's 1111, isn't it? It's called applications. Let's check the number while I'm at it. It is. The good news with this guy is that we've done a fair amount of it already. Let's start with one of the common questions that you get, is that you'll be given a function, let's say x e to the x, and it's going to be, I'm going to start off with a nice easy one. I'm going to center it at 0, so essentially it's a Taylor series, but all I'm going to find is t3 of x. Now, that will be f of 0 plus the derivative at 0, x over 1 factorial. The second derivative at 0, x squared over 2 factorial. And then I'll finish with the third derivative at 0, x cubed over 3 factorial. Isn't that a nice, reasonably short way to write down what we're after, right? That's what T3 looks like. If I asked you to find T2, wouldn't you only stop there? That would be T2 you're looking at. So to be able to fill this in, I guess I'll do my working on the next page. I need to find these 4 numbers. So I'll start off with my function, which is that guy. And f of 0 ends up being 0 times 1, which is just 0. And then I'll do my first derivative, and I'll do a product rule. And that's going to be 1 times e to the x plus x e to the x. And I would do that. And that would give me the first derivative at 0 ends up being e to the nothing times 1, which is 1. Okay. And then I would do the second derivative. And if I did the second derivative, can you just trust me that you end up with that eventually? And the second derivative at 0 ends up being 2. And then I'll do one more, the third derivative, and that ends up being eventually that guy, but you'll have to check it out. And the third derivative at 0 happens to be 3. Actually, that one would be reasonably easy, wouldn't it, to generate a Maclaurin series for? But I'm not going to. I'm going to use it to get that guy. So T3 of x is f of 0, which is nothing, plus the derivative, which is 1, x over 1 factorial, plus 2x squared over 2 factorial, plus 3x cubed over 3 factorial. Are you happy about where the 0, 1, 2, and 3 go, right? 0, 1, 2, and 3 go. Now I'm just going to make it look pretty. Don't need to write that. That's basically just x. They cancel out because 2 and 2 factorial are both 2. And that gets you 6, so 3 over 6 is a half. And we get that guy. Now, T3 of x is not the same thing as x e to the x. Wouldn't I have to do the entire power series to get the same thing? But isn't T3 of x probably going to be a pretty decent fit, right? Remember we did, oh, what did we do? The sine of nothing point 1, 2, 3, 4, 5, 6. Remember that guy? They tend to be really good fits, right? So let's look at some visual stuff, which is when make that go away, which is the point where I'm now going to make Desmos do its thing. So here we go. Put you in. Any questions in the chat? No. Okay. So got this fella. Go. So I am going to look at the original function, and we'll put that fella in. And the original function is y equals x e to the x. I should be able to just do e to the power of x. Great. Interesting shape. Great. Now, I'm only interested close to 0. So I don't know if you've used Desmos, but you can actually restrict the values of x that you sketch on. So this is how you do it. You do curly bracket. Since I'm interested in 0, I'm going to go -1 less than or equal to x less than or equal to 1. So that's basically how you restrict that. Then you put a colon and you rub out the y equals. It doesn't actually want them. And then I should be able to put in a curly bracket. And please tell me the thing has, what have I done now? What have I done?
-1.
Oh, thank you. I thought I typed it. There we go. There. Now, it just is a little bit easier to focus if there's only a bit of the curve, right? So if the rest of the curve's in there, it's distracting. So I'm now going to copy this guy. Oh, well, maybe not. I've changed my mind. I'm now going to put in T3 of x. And T3 of x is y equals an x plus an x squared plus 1/2, which I'm just going to call 0.5 x cubed. Would you agree it's a pretty good fit? Would you also notice that the worst fit is always at the extremes? Would you agree by the time you get to -1, you've got a problem, right? Now, I'm going to redo this guy with the restrictions so that we're kind of comparing like with like. So it's going to be curly bracket, copy all that so I don't need to type it from scratch. There. And now, cool. So let's talk about some truisms. Won't a T3 of x be a pretty good fit to the original function, most of its value, as long as you keep close to the center, in this case at 0. If I did a T4 of x or a T5 of x, would it be as good a fit or a better fit? What would be the truism here? Would a T4 of x, if I calculated a T4 of x, would it be a
better fit?
It should be, shouldn't it? And a T5 of x will be even better fit than T4. So the truism here is the more terms you use from your power series, right, in your T guy, right, in your Taylor series, right, your T4 or your T6 or your T10, don't you get a really good fit? And second point is that the errors are always going to be worse at the ends. So if I click on that point there, can I make it stay? Don't know if I can. No. And I click on that, no, this point here. Can you imagine me clicking on that point and clicking on the blue point? If I knew what those values were, wouldn't the error be the difference between the real value and what the T4 said? Okay. So now I'm going to return back to our notes and see if we can apply some of that to a question that you would expect someone to ask. And the question would go something like this. I have this function, but it's too difficult to calculate or whatever it might be, or whatever reason it is, and you're going to use T3 of x. And you're only going to use it in the interval -1 to 1, right? The question that someone might ask would be, I think that an engineer would call it the tolerance. We'll call it the error. What's the worst error I could possibly get, right? The error function is basically the function itself, take away what T3 of X says it is. Does that make sense? That's the real answer, and that's what T3 of X. Now, we tend to put an absolute value around it. Why do you think they do that?
So you stay around 0?
Well, not so much that, but just so your answer's positive. Aren't we only caring about how big the error is, not whether the error was a plus error or a negative error? Aren't we more interested in that? Now, we don't call it the error function. It's actually called the remainder function. And it uses R for remainder. And that's your guy. Now, in the question that we've just done, which is this guy, right? I would like to know what kind of error there were at the ends. Now, I tried to click on Desmos, so it wasn't really working well. Plus, Desmos probably only gives me the answer to 2 or 3 decimal places, right? And I'd like to be more accurate. So all you need to do, this is the numerical way of doing it, is find the error at the extremes. Right? Because I'm only going to use values of X in this range, can you, and we've seen it in the picture, wasn't the X equal 1 and the X equal -1 where all the stuff was happening, right? That's where the errors got significantly larger. And so if you find the value of the function at -1, so it's at -1 e to the -1, and then you take away, I'll just call it T3 of -1, and I'll get that answer as a decimal. And then I'll do it at 1. So what's that going to be? 1 times e to the 1, take away T3 of 1, right? That would be my second answer. And I'm going to get the calculator to do that. So I'm going to go into y equals, and the original function is x e to the power of x, okay, close the brackets. And then you take away all of this. So if you want to do it, you can do take away a bracket, an x plus an x squared, plus a half x cubed. Right, would you agree that I've just typed in essentially the remainder function, right? That guy, right, is him, and this is the T3. And then I'm going to go to second table setup, and I'm going to make sure that that ask is highlighted. As long as that's done, I don't care what the rest says. And then if I've checked that it is there, I go second table and rub out old stuff. And I'm interested in what's the difference between the two at -1, and what's the difference at 1. Now, in this case, do you see that the answers are what, 0.13 and stuff and 0.21 and stuff, right? Now, the bigger of those two is 0.21, agreed? Obviously, 0.21. So I can say this, if you want to use T3 of X instead of this guy, and you're only using values of X in the range -1 to 1, your answer, i.e. this guy, give or take 0.22 if you round it off. There's your tolerance. Not great, agreed. You know, the answer might be 12.9, but it could be as little as 12.7, 12.2, you know, that kind of thing, right? But at least I know that when I use this guy here, and I compare it against what the original answer is, isn't the most it's going to be out is about 0.2 and a bit. Now, I'm not going to do it, but I'm going to pretend I did it. and I did T30 of X. Imagine we did 30 terms. You'd get a computer to do that, but we did it. It shouldn't surprise you if the answer ends up looking like that. Now, if you want to program a function to do the sine of X, couldn't you just do a T30 of it? And won't that be pretty much as accurate as you need, right? You can have a little program just to do a little for loop and add all the terms up, whatever way you want to do it. It's not that difficult to write a program. And you would get a pretty decent answer. You know, I'm actually, that's probably an under exaggeration. The answer is more likely to be things like this. You know, 20 decimal places good. That's more realistic, I would guess. In fact, when we did it last time, wasn't the sine of X good to about 9 decimal places? Remember that guy? At least in the value I calculated. That is a pretty significant improvement on calculations, right? If you looked into the insides of any computer program that calculates things, e to the x, sine x, right, anything like that, if you look internally into what happens, aren't you, I would strongly believe that aren't you going to find one of these guys? It might be a T30, might be a T90, but won't it be there? Now, what's so clever? If you're a computer, can't you do 1 billion calculations in a second? Yeah, a T90 is nothing to it, right? It can do a T900, I bet you. So you can be pretty sure that your answers are good to a tolerance that no one would ever really care about. Are we good? Right. So for the last part of today, let's talk about, because we're going to do more of these T guys next time, but they take too long and I don't have enough time to do that. So let's look at problems with Taylor series. Actually, it's the same problem with both, but I'm just calling it Taylor series. Certain functions are not good, don't play well with the Taylor series, right? They don't converge quickly, they're messy, whatever you want to call it. So let's look at what makes a bad function to do a Taylor series on. We've already seen this guy. Be very, very careful if there's a vertical asymptote anywhere near where your center is, right? So can we pretend that this guy is at x equals 3? You could be quite happy in centering at 7. You could be quite happy at centering at 0, right? But don't ever center it at 3. And don't even center it at something like 2.5. Because isn't that function going to go vertical on you really quickly? And Taylor series doesn't play well with verticals. Second function that causes problems, and you should be really careful about them, are functions that do these things. Just curious, can anybody remember the name you give to a function that's got one of these little pointed things? Starts with a C.
Crappy.
No, that's your opinion of it. That's not the official term.
Is it conjunction? Conjunct?
Called a cusp. You don't want to do a Taylor series anywhere near one of those guys. So if you're going to create a Taylor series, probably the first thing you should do is put it into Desmos and look at it, right? And say, okay, vertical asymptote, make sure I keep away from that. Oh, one of those guys, keep away from that. Here is the third and final horrible thing that you want to keep away from. Functions that look like that. Now, I don't know how well I've drawn it, but that guy there has an x coordinate of 3. Why do you want to keep away from x equals 3 when you do your power series or your Taylor's or Maclaurin series for a function that looks like that?
It's a vertical S, it becomes vertical.
Yeah. And vertical tangent lines mean vertical derivatives. Vertical derivatives mean infinity. And infinity is not a good place to ever be near, right? So if you try to do a Taylor series, if you keep far enough away, you're good. But to give you an example, what would happen? Let's suppose I did a center there up at 5. My function would look like this. Can you see huge error when you get close to that vertical guy, right? The curve doesn't, the green one is meant to be my, whatever it is, my T5 or something, right? It fits good here, but won't it have a real problem trying to fit at that one? Now, if you did it here, and let's suppose you centered it here, you might get a really nice curve, right? And then, can you see the cusp is probably going to kill it, right? All weird stuff's going to happen. Trust me, I'm saying that's it, but it could be something even weirder, right? Bad news is going to happen. Vertical asymptotes, okay here. But what will happen is that your function will just forget the vertical, right? Or it'll curve through it. Can you imagine that at these points here, really close to the vertical asymptote, couldn't the y value be 1,000,000, but this is only 100, right? It will have huge errors. So we don't like them, but now you know that they're ones to avoid. Won't you avoid them in your calculations? Right? You won't pick a center too close to those bad places. And this is a good point, a good place for us to finish for today. Has anybody got me a good joke? So last name while we're waiting. Has anybody got a good joke to finish with? Since I've been getting a lot of slag off everybody else and not getting the appreciation that I deserve for my really cool jokes. Jeremy, I'm just mentioning, right? Nobody got anything for us? Jessica, you got one? Nothing. Michael?
I have one.
Oh, go for it. What
I
you
looked
got?
it up yesterday.
Okay.
A girl takes her boyfriend home to her parents. Her
Right.
parents don't like his tattoos and clothes and all that stuff.
Mm-hmm.
So later they tell her that they think he's a bad guy.
Mm-hmm.
And she says, well, if he's such a bad guy, then why is he doing 500 hours of community service?
That's so painful. I like it. That's a good one. Right. Bye-bye, everybody. I will see you on Thursday where we do more of these guys.
Hey, these power series remind me of something that I looked into like over the break, which was this series, which is called 3n+1, where you start off with a number. Say you start off with 1, it will be 3 + 1. No, 3n+1 will be 3. Yeah, 3 + 1, it'll be 4. And if it's a odd or it's a even number, you divide by 2. If it's an odd number, you put it back in the function.
Mm-hmm.
It has this weird thing where it goes straight shooting up and it comes straight back down. The same cycle, 4, 2, 1.
So it just repeats its answers.
Yeah, like whatever number you start off with might just lean you out to infinity, but it'll shoot right back down. And apparently for the last like 100 and something years, somebody has been trying to figure out what number to put in there that will make it true.
Wow. Somebody has got a lot of time on their hands.
Yeah. Well,
Yeah. Number theory, which it sounds to me like that's a number theory problem, are really weird. A lot of people have put conjectures. That's just a fancy name for, we think this is true, but we haven't been able to prove it. And if it's a big one, it actually gets named after the guy. So it would be like Gauss's conjecture and Macfarlane's conjecture. That
Yeah,
sounds to me like it's one of those.
Yeah, it has an actual name. I'm trying to remember what it was called.
Yeah, it's probably
Isn't it-
after the first guy who.
Isn't it called
Put the
3x
idea-
plus 1?
I have heard of 3x plus 1, yes. That might, well, that's a pretty boring name, but I do recollect that one.
Oh, it's called
Yeah.
the Paulatz conjecture.
Say that word again?
Paulatz.
That must be the guy who did it then, or maybe it's the name of some visual thing that's going on. Sounds to me like it's jumping away. There are some weird ones when you look into number theory about, what's one that I remember off the top of my head? Density of prime numbers. So if you take any 1,000 numbers, right, start to finish, there's going to be a certain number of prime numbers in there, right? Now, if you go from 0 to 1,000, there's an awful lot of prime numbers. But if you go from 1,000 to 2,000, there's less prime numbers, right? If you go from 2,000 to 3,000, there's less prime numbers. So the density decreases. And the question is, since we know that there's an infinite number of prime numbers, because there is, we've proved that, does the density function level off? Like, do you reach a point where you're kind of guaranteed at least one, let's say, prime number in any 1,000 interval of numbers? And nobody's proved that. They believe that the density prime function levels off. They're not quite sure what's what you're guaranteed, like, because it might be you need 100,000 numbers to guarantee a prime number. But there is a number out there they believe exists, but they haven't been able to prove it or find it. So yeah, those number theory people just have too much money and too much time. Because I can make up things that nobody can prove, right? And then call it the Robertson paradox or something and get other people to spend 50 years of their life doing it. And I'm at university getting a really great job. Oh, our professor did the Robertson paradox. He did? Yeah, well, he must be good then. No, he's just good at making up questions that nobody knows the answer to, right? I'm kind of jealous because I kind of would like that job. Wouldn't it be a good job? Right, bye-bye, guys. I'll hang about for any questions. Kira,
I
Have
you,
the rest of your day.
Thank you.
Thank you.
Kira, you liked my joke, didn't you? Oh, she's gone. That's how much you liked it. Right, who's got the first question?
So I had a question about the homework on
Mhm.
11.9
Coming up.
on question 7.
11-9 questions, and I'm having to close some windows, and then I'll be with you.
All right.
Well, okay, I closed too many windows, which I've been doing a lot of that today.
Tuesday's a long day for you.
Yeah, I start teaching at 8, so it is a long day. I mean, I have a few hours between my last class that finishes at 1 and this class,
Mhm.
but I have videos to prepare and grades and all the other fun stuff. Right, let's find this. 163. Gotcha. What section was 11.9?
Yeah. Problem 7.
Okay, I'm almost there. I'm in that. I'm looking for your question.
Mhm.
Usual reasons. So C. Oh, it must be the only one you couldn't do because it looks to me like you've done all the others.
Yeah.
So, did you say question 11?
7.
Oh, 7. 7. Okay, I can see it. So I'm looking at your answer and seeing what's wrong.
Must have botched up a number somewhere.
Yeah. Yeah. Okay. Okay, well, we'll talk about how you would do it, and you could tell me if you approached it this way. That might be,
All right.
that might make sense, and you can say, no, I didn't do it, in which case that'll fix it. I'm having problems finding you now. So I can see in a little box, but I need to get back my big window. So where the heck are you? Exit minimized. There, good. Now I got my window. At this time of day, yeah. Okay, so you have your first question, 7A, needs to be fixed because I think the mistake in 7A has caused the mistake in 7B, right?
And C.
So, okay, and as it keeps going, yeah, and probably C, you're right. So let's fix 7A, and then you can go back and maybe try B and C again and see if they work, right? So there's the guy. That guy, we're going to do a power series for him. And that power series is going to fit in here eventually. But we're going to have to use some sneaky tricks. The sneaky trick that we're going to do is I'm going to try and find a function. I'm going to call it g of x.
All right.
Right. And this function, g of x, when I differentiate it, I get that guy. In other words, I get f of x. So when I look at this guy, I would start off by thinking that function, if I differentiated it, would give me something very close to that one. Would you agree? What I find out when I try it out is the signs are wrong. But if I make that negative one, it fits. We good?
Yep.
Right. So now I'm going to figure out how to get the power series of that guy. And then I'm going to differentiate that power series, and that's what I'm looking for. So that's my goal.
Okay.
Find the power series of this fella, then differentiate that power series, and we're done. So the problem with this guy is the 2. So I'm going to pull it out. Are you happy about this and that are equivalent?
Yeah.
Right, 2 gets me that, 2 gets me x, the negative, I might as well give it to this guy. So we've basically got a negative 1/2 of this guy. So it's negative 1/2. And this guy here is negative 1 to the n, 1/2 x to the n. And that's going to go from 0 to infinity. Are you comfortable about the substitution trick for the 1 plus x, which is this guy?
Yeah.
Right. So now I'm going to make it look pretty. And what do I get? I get x to the n. 1/2 to the n is much better written as 1/2 to the n. So that's what I did.
All right.
And now I'm going to bring in this negative and this 2. So everybody is inside the sigma. A negative 1 added to this just gives you 1 more. That guy is still x to the n. And a 2 added to this gets you 1 more. So we have found our power series for g of x. So far, so good?
Yep.
Right. Now I'm going to differentiate that guy. And what you're going to get is essentially multiply by the power, reduce the power by 1. Looking good?
Yes. It's.
That's pretty much what you've written. Great? Okay. Now, technically speaking, this starts at n equals 0, but n equals 0, this whole thing is 0. So I'm going to move it to n equals 1, which does the same job. And typically, that's what you should do. When you differentiate some, right, that has a 0, just start at 1. It takes care of the little idiosyncrasies of what the first term might be. And then I'm going to do some other algebra to finish this question off. That definitely looks good, but it's not considered good enough style points. So what I'm going to do is I'm going to change this guy to x to the n, the way we'd like it to be written. Now to
I have a
do that,
question.
yes.
Oh, never mind. Now I see how you got that. Never mind.
So I'm going to change this to n. And the way I'm doing that is every n is going to be replaced by n plus 1, essentially.
Hmm.
So this guy becomes n plus 1. This guy becomes n plus 1 plus 1 becomes n plus 2. And this guy becomes n plus 1 plus 1 becomes n plus 2. Are you good with that?
Yeah, I think so.
Right, so all the n's get replaced with an n plus 1, and this is what you get. And when you do this, turning an n into an n plus 1 or whatever, you have to fix this fella. And what happens is, if you add 1 to all the n's, the sigma doesn't get to become 2. You compensate by removing 1 from it. That gets everything balanced. The analogy I give is like a seesaw, right? When one side goes up, you have to reduce the other side by 1 to match.
All right.
And that guy should be the correct answer. And as far as I'm concerned, it is. But WebAssign added in just a little idiosyncrasy, because I guess it's not that bright because it's a piece of software. They called it that.
So I'm trying.
So the only thing I changed was -1 to the power of n plus 2 gets replaced by -1 to the power of n. Let me convince you why that's okay.
To me, that just seems it's the exact same thing. So.
It is the same thing. It's that guy. That guy's 1, and that's what you get. Evidently, WebAssign didn't like n plus 2, maybe, or maybe it would. Maybe it'll take that. I'm not saying it didn't, but that's the answer that they have in front of me. So that's
Funny.
the one that they're looking for, right?